Hello everyone, so today we're going to go over section 11.3, determining probabilities using fractions. So to begin, we're going to talk about the two different probabilities. The first one is experimental probability, which is based on experimental results. Okay, the second one is theoretical probability. This is where we calculate a probability of an event by counting the favorable outcomes and the total number of outcomes. Another important concept when it comes to probability is simulation. This is when we model a real situation using an experiment of some kind. Oops. Okay, so we'll begin by going over the theoretical probability of independent events. Okay, recall that the probability of an event, let's say probability of an event called A, that will be equal to the number of favorable outcomes divided by the total number of outcomes. Now, if you have multiple events and they are independent, so let's say A and B, then the probability of both of them happening will be the product of the individual events. Okay, you'll also see the symbol, this symbol right here used for AND. So I'm just going to write it here, the AND symbol. Okay, so we're going to flip a fair coin and roll a fair die. And as usual, if we don't specify the die, it will be six-sided. Probability of flipping heads will be 1 out of 2. And the probability of rolling a 4 will be 1 out of 6. So if we are to look at those two probabilities, and since flipping a coin and rolling a six-sided die are independent events, the probability that both of these will happen is simply their product. So 1/2 times 1 over 6, which is 1 over 12. Similarly, what's the probability of flipping a coin getting tails and rolling an odd number? So here, just recall that an odd number on a six-sided die, there are 3 of them, 1, 3, or 5. So that's half of the outcomes, or 3 out of 6 outcomes. So if we were to calculate the probability that we would flip a coin, get tails, and roll a six-sided fair die and get an odd number, that will be t and odd. Probability of tails is 1/2, and the probability of an odd number is 3 out of 6, which is also 1/2. And so the probability that both happens is going to be 1/4. Okay. Next up, we're looking at the probability of rolling a 6-sided die and rolling a 6, and we're going to do that twice in a row. So that will be the probability of 6 and 6. Probability of 1/6 is 1/6. Probability of a second 6 is also 1/6 because the die rolls are independent of each other. So double sixes will have a probability of 1/36, which makes sense if you were to create a table for the sample space. There are 36 different outcomes, only one of which is 6 and 6. What if we roll 3 dice? Well, then that would simply give us, oh, sorry, rolling a 5 3 times in a row. So that will be 5 and 5 and a third 5. You know, just write 3 5s. And of course, each of those would have a probability of 1/6. So you simply multiply 3 of them together, and it is quite unlikely you will get 1 out of 216, which is pretty unlikely, which makes sense. Let's continue on the next part. Oh, yes, this is the experimental probability question. It says here, LeBron plays basketball for the school team. His stat shows he has a 75% chance of making his first foul shot and a 50% chance of making a second shot. We're going to change the second number here to something that's more reasonable, because statistics shows that basketball players tend to shoot better on the second free throws. I'm going to change this to 80%. So fairly good. So a number that makes more sense. What is the probability that LeBron will make both of his shots? Well, we create a simulation to find the experimental probability because, well, we're not going to be able to find a 75% free throw shooter and shoot 3 throws. So we're going to use a simulation instead. So in this case, we're going to use a random number generator. From 1 to 100. So if it's 75%, so anything from 1 to 75 would be a made foul shot. Otherwise, it's not. So let's generate some random numbers here so that we yes, no, yes, yes, yes for the first 5. Yes, no, yes, yes, yes. And then 5 more. Yes, no, yes, no, yes. Okay. Yes, no, yes, no, yes. Okay, so you can see how using a random number generator uh, can help assimilate these free throws. Anything that's from 1 to 75 is a make. Anything from 76 to 100 is a miss. So second foul shot, instead of just using the random number generator again, I already have some results made for us. So it was no, no, yes, 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 no, no, yes, and yes. All right, so now because 10 foul shots really, or 20 in total, really isn't that many, there's a chance that we don't get a number that's close to the 80% or the 75% that we had used to run this simulation. So if you look at the second foul shot, this is supposed to be an 80% chance of success. There were only 6 successes. But that's kind of expected. You're not going to get 8 every time because the sample space is really small. Both shots good. That's no, no, yes, 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 and then yes here. and then 3 more no's. Okay, so we recorded the results in table A. What is the experimental probability that he will make both shots? We can simply count. There are 5 instances where both shots were good. So that would be 5 out of 10 or 50%. Okay, what is the theoretical probability that he will make both shots? Now we're going to make the not good assumption, but it will be good enough for now that the foul shots percentages are independent of each other. They really are most likely not. But we do have 75%, and for the first shot, and then the second shot is 80%. And so we're going to multiply those together, and that will give us 60%, or 0.6, which is 60%. Okay. So again, because our sample size is so small, we are going to get something that's not close to being the same. Okay, assuming independence, which is again not a good assumption. Okay. So it's going to talk about the next example a little bit. Again, we're going to use a random number generator, so I'm not going to show that part. But I do want to talk about how we can use different objects to run simulations instead of having a like a web browser with a random number generator on it. So it says here Andrew has a regular coin and a 3-color spinner. So the colors were blue, let's say red here, and green. And you can see that 1/3 of the circle is blue. Okay, Andrew wants to calculate the probability that he will flip the coin and get heads, and spin the spinner and get blue. So if you are going to run a simulation, a good way to do this is to use a single die, and then we can say 1, 2, and 3 are heads, and 4, 5, and 6 are tails. So every time we roll a 6-sided die, we simulate a coin flip. So we don't need a coin to do this, but we will need a die. However, we can use the same die for the second part as well. So we can simply say that, let's say here, 1, 2 could be the blue. 3, 4 could be red. And 5, 6 could be green. So we can use a single die for simulating events that have 2 equally likely outcomes, 3 equally likely outcomes, and 6 equally likely outcomes. You can also do it for 4 and 5, but then if you get numbers that are not included, so let's say, for example, you are trying to simulate an event that has 4 equally likely outcomes, so you assign the numbers 1, 2, 3, 4. 5 and 6 will have to be re-rolled. So, however, if you have 2 outcomes, or 3 outcomes, or 6 outcomes, you don't need to have unassigned numbers. So, anyways, the rest of this is just more of the finding experimental probability and comparing them to theoretical probability. And the idea is, if you run a larger and larger number of simulations, those two numbers tend to be close. And that is to say, as you do more and more experimental, simulations to find the experimental probability, it tends to trend towards the theoretical probability. Okay, but that's it for today. So thank you for listening.